Hey, so in this video I want to go over two types of problems that would have to do with calculating pHs, either at an equivalence point in a titration, or just simply asking what is the pH of a salt solution. So we'll start off with this problem. What's the pH at the equivalence point if you neutralize 50 milliliters of 3.0 molar ammonia with 1 molar of an HBr solution? All right. So first of all, where does this pKb come from? This comes from the data booklet. I've actually printed out these. You'll be having your own copy of this. But I want you to get very comfortable with how to get that information from the direct source, because that's going to be how you have to do it on the exams from here on out. So start off by writing down the neutralization reaction. All right. Hopefully you realize ammonia is a base, and it would react with this acid right here to make the ammonium salt. All right. And again, this would be dissolved in water. So you wouldn't have this right here. You would actually have ammonium NH4 plus, and also you would have Br minus. These would be individually swimming around in the solution. But as before, if you were to take this solution and completely evaporate it, you would be left with this white solid, which is pure solid ammonium bromide. All right. So what would this neutralization look like? All right. This is going to be the opposite of a weak acid curve. All right. So we're starting off with a weak base. All right. So you'd assume that it starts with a pH which is above 7, but not way high, because this is not a strong base. All right. pH would probably be around something around 10 or so. And it would come down. We have this buffered region again. All right. So, and then we're going to get this sharp drop off. This would be the equivalence point. All right. So this would be where we've added exactly 1 mole of this for every 1 mole of this. All right. So what are some things that we need to know about this problem? All right. So first of all, we need to figure out how many moles of the ammonia we have. All right. So if we take 0.05 liters of that, and we multiply it by, I use a little crossbar. Again, this part of the crossbar right here, that's 3.0 moles per 1 liter. All right. You could cancel out your liters, and that would tell you that you get 0.15 moles. All right. So that tells us that we have 0.15 moles of this. And so since we have a 1-to-1 ratio, we know we would need 0.15 moles of this. And that would allow us to get 0.15 moles of this. All right. By the way, I should have mentioned this at the beginning. Feel free to pause the video and see if you can do this from start to finish without any help. All right. A lot of these are concepts that we've already done, and I do think that you learn this the best if you try to do it yourself and then figure out where you need help. Okay. So where to from there? All right. Well, if we have 0.15 moles of this, well, what does that mean about how much of the HBr solution we would need? All right. So if we've got 0.15 moles of this, and we have it in the form of a 1.0 molar HBr solution, that would tell us that we need 0.15 liters, or another way of saying that is 150 milliliters. All right. So what we can do with that is figure out what the concentration of this salt would be at the end of the neutralization. Remember, it's going to be the combination of the base solution that has now had an acid solution added to it. All right. So we know that that solution is going to have 0.15 moles of ammonium. Sorry, that should be ammonium bromide, not ammonium chloride right there. So sorry. So you're going to have that much of your ammonium bromide, and we're going to have that in 200 milliliters of solution, which is the same as 0.20 liters. All right. So where does that come from? Well, it came from the fact that we had 50 milliliters of the starting base solution, and we added 150 milliliters of the acid solution. All right. Again, this should be HBr, not HCl. All right. So those two add up to 200 milliliters, and we could calculate that the molarity would be 0.75 molar of ammonium bromide. All right. So where are we going to go with that? We are going to write down what would happen to this stuff right here if you had it as a solution. All right. So remember, ammonium is just the ammonium, the NH4 plus. That is the conjugate acid of a weak base. All right. So that is the conjugate acid. It would be expected to react with water to make NH3 plus H3O plus. All right. And we're going to be able to do the same type of start, change, finish that we've done before. So we need a little information having to do with NH4. All right. So again, how do we find information about these particular chemicals? All right. So I'm going to go ahead and rewrite this reaction at the top here. All right. And so essentially we need to know information about both the base and the conjugate acid. Actually, what we would need is information about the conjugate acid. All right. So before showing you how to do that, hopefully you can come up with an idea of how to do that. But what I'm going to do if you're having trouble is first give you a little hint. All right. This is this shows a page from the data booklet. All right, and I'm going to give you a hint that there's some useful information on this page. All right, so if you haven't done already, take a look at it and see if you can find something useful that could be used in this problem. All right, and okay, so if you haven't found it yet, it has to do with this right here. This is ammonia, and it mentions ammonia's pKb. All right, so what does that mean about ammonia? We would know its pKb. And if we know its pKb, we can calculate the pKa of its conjugate acid. So the conjugate acid would have a pKa of 9.25. And with that conjugate acid, we would know the Ka of that conjugate acid. All right. So going down here, we have these values right here, and we just figured out what the Ka of this particular conjugate acid is. So we could take that value, which we calculated, and we could do the same standard treatment of it. And I think this should be familiar by now, eventually getting a pH of 4.69. All right, and that's what you would expect. All right, if this solution has a weak acid in it, you would expect that it would have a pH which is less than 7. Okay. So in the next problem, it looks like a totally different type of problem, but what I hope to convince you of is it's essentially the exact same type of problem that we were just doing. All right, so this says what's the pH of a resulting solution if you dissolve 7.54 grams of sodium dichloroethanoate in 200 milliliters of total solution. All right, so at first you'd say, well, this is just making a solution and figuring out what the pH is, versus these types of problems right here, which is figuring out the pH of a solution at the equivalence point. All right. So hopefully you realize that the connection is that when we do these neutralizations, essentially what you have at the end is a solution of the salt of this neutralization, and that you can figure out the pH essentially in the exact same way that you'd figure out the pH of a salt solution. All right. So if you look at the language here, sodium dichloroethanoate. All right. This is a salt. All right. This is something that we could make by reacting an acid with a base. All right. So I'm going to see if you guys can maybe figure out something about this with a little help from the data booklet. All right, and take a look at the information here and see if you can maybe figure out the information that's needed. All right, so if you're stumped, let me just point this part out right here. Okay, sodium, so the dichloroethanoate. All right, notice this ends in 8. All right, And remember that the relationship between 8s and ics, all right? So if you have sulfuric acid, which is H2SO4, remember, since it adds an ic, if you replace that with the ic with an 8, that gives you the polyatomic ion, the stuff without the hydrogens, all right? So this right here, if we remove the 8 and we put an ic acid after that, this shows you that all this is the conjugate base of dichloroethanoic acid, all right? And we have dichloroethanoic acid right here, and it gives its pKa, all right? So we should be able to deal with that, all right? So taking a look at, all right, so this right here is sodium dichloroethanoate, and that is nothing but something that if you took the dichloroethanoic acid and reacted it with sodium hydroxide, you would get sodium dichloroethanoic acid. That's exactly what we have right here. Notice that like the sodium, when you have sodium salts of weak acids, sometimes you put the Na plus on the front, sometimes you put it at the end. It's not as important as when you're doing the strong bases. All right. So what we can get from the data table is that the pKa of this right here is 1.35, and that would tell us that the pKb of this conjugate base is 12.65, and from that we could figure out the Kb of this material right here. All right, so we could calculate the how do we go from there? Well, we're just going to use a little stoichiometry. All right, so if we've got 7.54 grams of that stuff, all right, we have a mass. We could figure out the molar mass of that particular formula, and that would tell us how many moles we have. All right, we also have a volume, so therefore we should be able to calculate a molarity. All right, so we calculate that molarity right there. We have a solution which is 0.25 molar in this material right here. All right, and so just by comparison, isn't that what we did when we were doing these neutralization problems? We got to a point where we had the molarity of a solution of that salt. All right, and the only difference is this is a salt that resulted from an acid-base neutralization, and this is a salt that resulted simply from taking some of that pure solid salt and dissolving it in water. All right, so we can do the calculation the same way, realizing that it would be a weak base. This is the reaction that would happen: start, change, finish, start, change, finish. We have these materials right here, and taking the pKb, which we calculated earlier, that would equal x squared over this. Again, we're going to do the same treatment where, since it's a weak base, we could assume that 0.250 minus x is roughly the same as 0.250, and we could eventually get to the pH right here. So notice that this is close to being neutral. All right, so how could we rationalize that? Well, if we take a look at the original situation, this acid right here had a pKa of 1.35. That's a very low pKa. So that means that it is a relatively stronger weak acid. All right. So the stronger that weak acid is, the weaker the weak base it would make over here. So if it is a relatively weaker weak base, you would expect that the pH would not be that incredibly basic. So it is slightly basic, all right? It's above 7, but not that much.